Also, thanks for having me at the workshop and for letting me present on this topic today. It's not so much of a detour, as you'll see. It kind of falls right in line with the other topics that have been discussed in a lot of different ways. Um, so one of the things I want to kind of bring up from this initial image is that in sample composition, specifically for astrobiology, we have to think about scales and also think about data quantity from different missions and what is actually available for these different training sets. So I kind of chose this selection to highlight things like Europa Clipper and Rosetta, and you can see OSIRIS-REx sample there as well, and Dragonfly, which is the mission that I'm working on, and then comparing those missions to comets in the outer solar system to Mars that's been much more highly studied. So those kinds of disconnects and mismatches in data sets and data quantity are going to be pretty crucial for building any kind of foundation model. So then a quick overview of what I'm going to be talking about, a little bit of what types of samples actually could be relevant to astrobiology and some examples of what might be biosignatures, a overview of generally spectrometry versus spectroscopy, which is a huge topic, and each one is its own textbook, but I'll do my best. And then a couple little special topics that I think are important to consider from my personal experience, and then going from that to conclusions and future outlooks. So first, starting with sample considerations, thinking about type, scale, and potential biosignatures at each scale or sample type. So, in this kind of general field of astrobiology, we can scale all the way out to atmospheres, so planetary to regional scales, with biosignatures being potentially unstable compounds like an isoprene or methane fluxes at specific seasons. You could also have, in the more planetary to even micron scale, things like oceans, rocks, and sediments, which again can have biosignatures that are in the rock themselves. You can have a biosignature that's in the ocean itself, such as potentially even oxygen as a biosignature. And then also specific mineral phases can be biosignatures, as well as extant cellular life for any of these cases. So these are all things to consider for astrobiology. Then kind of subsectioning into the specific of organics, often within oceans, rocks, and sediments, can be also regional to micron scale, with potential biosignatures including organic molecular biosignatures, or the kind of classic like biomarker, or like a steraine or a hopane. You can also have organic enantiomeric excess as a biosignature, as well as, of course, DNA and RNA, which, if they're detectable, would be a clear sign of extant life. There's also maybe just as well studied, but not as well considered on my side of things, would be things like aerosols, which can also be regional to micron scale. And I know Connor Nixon can do a lot of work on, I think he was in earlier, and he may still be here, who can speak to this a lot more than I can. But you can have things like extant organisms entrained within aerosols, or potentially entrained organics on those aerosols as well that can be biosignatures. And the final thing I want to note is something that, as a geologist in a previous life, isn't often noted but is extremely important, which is the scale of time. So on the right, the image I've included is of the geologic history of the Earth, showing different types of biosignatures that are detectable at those different scales. Noting specifically that at each time, you would have a different type of biosignature, and different types of samples can incorporate different types of biosignatures in different ways. So, the reason as a geologist we like rocks and organics is because those rocks hold the history of potentially millions of years, whereas a sample of a particular time could only potentially give you a false positive or false negative in that specific time. So time is always extremely important to consider. I just want to make that a point. Um, Another really important consideration is sample pre-processing. So I specifically work in laser desorption mass spectrometry here at Goddard, where we can take a sample and essentially shoot it with a laser, and we can see what comes out. And there's a lot of real large benefits to shooting a rock or a powder with a laser and seeing what comes out. But when you do that, you end up having a lot of time on the data analysis side, because if I have a rock with multiple types of inorganic phases as well as organic phases, and I shoot it with a laser, there's a potential where I'm going to have a mass spectra of all those different types of samples in one mass spectra, which is really hard to deconvolute and can be extremely complex. Um, on the other side, if I take that rock and I crush it and I extract all the potential organics out of it, and then I separate those organics into different fractions like apolar or polar, etc., I can then analyze each one of those fractions in a different instrument and get a better handle on each specific type of data or specific type of potentially organic compound that's in that sample. But there is a lot of pre-processing that goes into that, which is really difficult to do on other planetary bodies. So for all sample analysis and sample composition analysis, this dichotomy between the resource intensive sample preparation and the resource intensive data analysis is a really important consideration, and both have a value, which is a theme I'll come to in a second as well with other analyses techniques. Specifically with spectrometry versus spectroscopy. So on the left, I'm showing a spectrometry data set, and on the right, I'm showing a spectroscopy kind of like vague data set that I've just kind of pulled off the internet as examples. So in spectrometry, these techniques can be sometimes semi-destructive. So, you take a rock and you shoot it with the laser, that one little laser spot may be destroyed, and you can't reanalyze that one spot, but you could analyze multiple spots across that rock, especially with the spot size of 2 microns for an analysis. You could analyze a rock for an entire PhD and still not run out of sample, which is what I did. And on the more spectroscopy side, these techniques can be fully non-destructive, so you can get some information without destroying the sample at all. But again, as you go from this non-destructive to destructive analysis, what you gain is the ability to separate out different parts of the sample. So there's always going to be a trade-off for both spectrometry and spectroscopy. One, I think, kind of big note for spectrometry versus spectroscopy is that in spectrometry, you have to produce and detect ions essentially in the same location. So you can't remotely do spectrometry, whereas spectroscopy, of course, you can do remote sensing. So that is a pretty big difference to note. But then some of the similarities between the two different techniques. In both techniques, samples can be whole, crushed, or extracted. You can have molecular composition available in both techniques, and imaging is available in both techniques depending on what kind of analysis you're doing. So to first zero in on mass spectrometry and how mass spectrometry actually operates, one of the first things you have to do is generate ions. So you have to create a charge on the different compounds that you're trying to actually detect in order to detect them. So on the left hand of this figure, I'm showing these samples that we've created earlier, which is an extract with different fractions separated, as well as a powdered sample and a whole rock sample. For the extracts, we can actually, we have to volatilize the products a lot of times, and then we can either separate those with chromatographic methods, getting each compound to come out individually, to then ionize each compound to then detect its mass spectra in order to give it a certain fingerprint. We can also do a similar thing with powders. So if we have a rock powder with a lot of organics in it, we can actually pyrolyze that sample, and we can mix it with different derivatization agents to then put that pyrolyzed sample or volatilized sample through chromatographic separation, and then again into an ion source, into a different mass analyzer and detector. So both of those techniques can go through this chromatographic separation step. But the other type of analysis we can do is direct sampling and ionization. So taking a whole rock or a sample, again, shooting it with a laser or a different high energy beam, and then detecting those different compounds that come out directly. So those different ions that come out directly. A couple of things to note here are the ionization source is going to play a huge role. So whether you're ionizing these compounds via a or electrospray or chemical ionization or plasma sources versus laser desorption or secondary ion mass spectrometry. I'm sure you've all heard of these techniques, and some of you are probably very familiar with them, if not experts in them, but they all do produce different types of ions. And so this is a large consideration, is even though we've sent a lot of mass spectrometers into space, those mass spectrometers are often operating under different principles. The other thing to consider is the mass analyzer is going to play a huge role. So a different quadrupole versus a time of flight versus an ion trap versus an Orbitrap are going to produce vastly different kinds of data. Even if you have a sample ionized via GCM or analyzed via GCMS and electron impact ionization into a quadrupole versus a time of flight mass spectrometer is going to produce a different resolution of data sets. So these are all extremely important to consider when actually thinking about this. So no matter what type of mass spectrometry you do, you're going to produce essentially just a 2D list of M over Z values or mass to charge ratio values. And you can make different mass to charge ratio intensity values all the way from tens of Daltons to hundreds of thousands of Daltons. So mass spectrometry is very versatile, depending on what kind of mode you actually use. But major considerations is that, again, the mass resolution, or essentially the peak width, so kind of showing here on this bottom image, the width of a specific peak driven by an ion or a group of ions, is really dependent on the mass analyzer that you use. So one type of instrument can produce a single peak, while another type of instrument can produce multiple peaks. And this type of comparison is actually pretty, it's non-trivial when you're doing machine learning, especially, and in comparative data analysis. So even within the same instrument, you can get these types of differences. So data reduction strategies are absolutely necessary. Also, for all mass spec analysis, calibration and normalization is an absolute must, and this needs to be considered as potential sources of differences in data sets. Even if you have the same data set and you calibrate it different ways, you can get different types of interpretations. So all this to say, all spectra is often interpreted by human individuals, and that interpretation can be difficult, so that having some benchmark or way to judge those different spectra would be really important, especially for this foundation model. And a last step on mass spec is that new developments are constantly happening in mass spec analysis, and there's not always ways to gauge those new developments, or I'll get into this a little bit with NIST, but there's not always ways to know how you can actually judge those new developments in mass spectrometry currently. So it could be a field for us to expand into. And I just wanted to highlight, this is some of the top SIMS mass spec I've generated before. And when I'm talking about it being difficult to interpret, each one of these samples this is one sample with a lot of different types of spectra that are separable via ML, but it's really hard to tell them apart just one person at a time. So, this type of larger scale foundation model, in order to help interpret these types of data sets, would actually be extremely valuable and could not denoise, but could find some of the real value in data sets that have already been produced. So it's a potential avenue for growth there. And then to go into spectroscopy, which I'm much less familiar with. I'm very much a mass spectrometrist person, but in spectroscopy, the general operating principle is you use some input of light and then detect either what has gone through, so what has been absorbed by your sample, or what has been reflected from your sample. But the big thing to note here is, a lot like mass spec, the different types of spectroscopy produce different types of data with different types of information. So here, this questions the chat we'll get to. So here at this point, I was showing IR, where you can actually shine a light source through a sample and observe what's been absorbed by your sample to get some sort of spectra there. Raman is a very common technique for space analysis. So shining a specific incident or specific frequency of light at a sample and detecting what has been scattered that's different from your initial type of light. And then SEM-EDS is using an electron beam to do something similar, but you're getting characteristic fragments so far as atomic composition from those samples. But kind of here on this bottom left is the main point of this chart, which is, although we often use spectroscopy as a term, and think about it in those terms if you're not a spectroscopist, each type of data analysis produces a vastly different type of data, which is going to be very hard to compare across instruments. Similar to mass spectrometry, the spectroscopic data that's produced is 2D list of intensities or observed reflected light values. So the data itself is not crazy to handle in any type of instrument, depending on how many data sets you actually have. You can get information on functional groups or mineral elements or structures, so very valuable data. But again, these spectroscopic techniques produce very different types of information, some qualitative and some quantitative, and some semi-quantitative, sort of in between. And the spectra can be extremely complex, considering something like a mixed natural sample that has rocks and organics in it. So those problems don't go away, but hopefully, even though these spectra do require a great deal of interpretation, ML and AI can actually help with that. So a couple little special topics I wanted to hit on would be some insight from NIST and GCMS. using EI. So NIST is like, if anyone here is a GC person, you've used the NIST GCMS database for sure to help identify your spectra. It is the gold standard. NIST has produced mass spectra of isolated compounds using electron impact ionization and exactly 70 eV for decades. So they have this vast database where you can take your instrument that has the exact same EI source in it or type of EI source in it, and hopefully your compounds are not co-eluting in the GC column, and you can then compare your spectra to this NIST database to say, oh, at a 97% mixing rate or matching ratio or reverse match ratio of 60% or whatever, I can at least somewhat say what my compound is. So NIST is great for exactly that type of thing. But what happens when you want to develop a new type of mass spectrometer, or you're sending a mass spectrometer to space that has been shrunken and changed in a lot of different ways in order to make it flight ready? Those NIST databases become not useless, but a lot less useful. So it's something to consider is we don't have these types of databases. And in my opinion, the development of instruments is not going away as technology progresses. So I think having a way to, if not replace the NIST database, augment these types of databases with AI is extremely valuable for enabling and progressing and furthering the progression of instrument development for astrobiology and for, I mean, honestly, commercial instruments as well and industry wide. Here, I'm not going to go over this whole slide because I don't want to kill our time, but I do want to just touch on what I'm showing here, which is something we talked about before, which is sample scales and heterogeneity. So this is a sample I analyzed using TOF sims, showing these kind of like small 500 by 500 micron windows of spots we've analyzed, looking at specifically these sterain biomarkers, which are specific biomarkers for eukaryotes. And even in these rocks that have extremely high total organic carbon content that have never been heated, so my biomarkers have never migrated through, there's still in regions that have organic matter, a huge variation in where these different biomarkers are at the scale of tens to hundreds of microns. So when you're talking scale of heterogeneity, it doesn't go just from planetary to regional to hand sample size. It goes from hand sample size to a micron away, you can have a detectable biomarker, and then 1 micron from that or 10 microns from that no longer have that kind of biomarker detectable. So something to consider. The other thing I want to point out here is that from these data sets, we can produce in TOF sims in this commercial instrument upwards of 62,000 mass spectra in a few minutes. So the ability to produce the data from these instruments is there. What we can do with it is, I think, one of the questions we can hopefully drive to with parts of this workshop. And here I just wanted to highlight that mass spectrometry and spectroscopy data sets are very different and they produce different types of data. But we have shown in recent publications that they are comparable. So that's not that these data are, they augment each other, and they're both necessary, but they are actually comparable through machine learning techniques. So the ability's there. It's just a matter of, can we actually harness it? So then just the final kind of conclusions and talking points. Both mass spectrometry and spectroscopy produce unique and comparable data sets that are going to be important for potentially locating and confidently identifying biosignatures. For spectrometry, instrument architecture is really important to consider. And for spectroscopy, the type of information potentially even obtainable with a given instrument is really important to consider. Looking forward, I think the rapid pace of technology really points to a future with a lot of data, potentially high quality data returned from in situ missions of other planetary bodies, but we're not going to have a NIST-like database to compare those spectra to. And a really important note that I don't know if it hit hard enough is that for both spectrometry and spectroscopy, identification of single compounds and complex mixtures, which are inherent to natural samples, is a current roadblock for progress, but something that ML has shown the potential to help with. So just my prediction is that the application of AI and ML to the large amount of data that we're going to be able to produce going forward by mass spectrometry and spectroscopic techniques will actually pretty much revolutionize what we can do for in situ analysis, both on Earth and for ET analysis for planetary samples.